Okay, so for this particular problem, we're trying to find the average value of the function on this interval right over here. So I want to find that interval, or assuming the average value of the function over that interval. Let's understand what that means. Now I've graphed that over here and I actually showed you a little bit of the Desmos commands that I used to color this in. Here's the graph, kind of an interesting looking graph if you actually did look at it beyond the interval 0 to pi over 2. But what we're interested in is the average value of this function. Now to get that, what we have to do first is integrate the function from 0 to pi over 2, and then we're going to divide by the length of that interval. So to set that up, we go over here. That's going to be 1 over the length of the interval. So that's this right here. Let's see if I can make that a little bit better. 0 times the integral from 0 to pi over 2 of e to the sine of t cosine of t dt. Now, just a word of caution on your remaining exam. I would appreciate seeing mundane things like, I don't know, an integral symbol or limits. It does make it easier for me to grade. Now, out in front of the interval, I can simplify that ratio as 2 divided by pi, right? Because dividing by a number is like multiplying by its reciprocal. Inside the interval, or excuse me, inside the integrand, I don't know what the antiderivative of this is off the top of my head, but I can make a U-substitution. So let's see about doing that. That's going to be, well, let's see, any suggestions for U? So there's two possibilities. You could pick cosine, pick sine. Now, if I pick cosine, then I get dt, or excuse me, actually du equals negative sine of t dt. But I don't have a negative sine of t dt here. So that's not really going to work in terms of figuring out, well, what I should let u equal. It's just not going to work. It's not a good u. So what's another possibility for u?
Sine t.
Sine of t. Thank you. Wonderful. So sine of t is our u. That means du by dt is going to be cosine of t. And then if I multiply that equation by both sides by dt, I get cosine of t dt. That's perfect because that matches here what I have here. So let's continue with our U-substitution. What I would suggest is that we change our limits of integration. U of pi over 2. Well, what's the sine of pi over 2?
1.
1, thank you. And the u of 0 would be 0. So I can rewrite my integral this way. As the integral from 0 to 1 of e to the u du. Now, if you don't want to change your limits of integration, that's fine. But if you don't change your limits of integration, then please don't write 0 to pi over 2 here. Because 0 to pi over 2 is for the integral when you're integrating with respect to t. If you're integrating with respect to some other variable, then just write a and b unless you're changing the limits. So that's 2 over pi. And let's see, this is going to be, well, we're done integrating, so we'll write a straight bar, 0 to 1 of e to the u, which is 2 over pi, times e to the u, or e to the first power, minus e to the 0 power, which of course is 1. 2 over pi times e minus 1. So how's that one looking?
Good.
Now let's make sense of that here. Up above, I actually drew in the line y equals pi over 2, or 2 over pi times e minus 1. And let's think about what that line means. That line is the average value of the function. Now, does that make sense for our particular function? Well, the function starts out a little bit lower than that, then goes up, and it stays up above that line for a long time, then eventually comes down a lot. So theoretically, if I did this right, if I calculated the area of this shaded region here, then that area should equal the area underneath the curve. But overall, that this is the average value for that function. And it looks reasonable, I think. I don't think that that looks unreasonable at all. So, okay. How's that one looking for the first problem here?
Good.
Doing okay? All right, yeah. Thank you. I've got another one. I don't have a nice graphic for this one, but I'm hoping that this one worked out pretty good with the graphic and reminds you of what you're finding when you're finding the average value of a function. Let's look at this one. The the average value of this function over the given interval. Well, let's see. So we're gonna have to do another integration. And it helps if I click the right thing here. This time, what are my limits of integration gonna be?
3 to 7.
3 to 7, thank you, of t over the square root of 7 plus t squared dt. Now again, we're faced with an integral for which we don't know how to find an antiderivative, at least directly, but we can do it indirectly with a little U-substitution. What would you suggest U equal in this case?
7 plus t squared.
Good, 7 plus t squared. Now, kind of the hint in that is that when you differentiate a polynomial, and right down here, we've got a polynomial, the degree goes down by 1. So if I have a squared term, then I can look for something that has, say, I don't know, a first power. And then that could be my du if my first choice was u. So, okay, good. Let me get rid of that. If du equals 7 plus, or excuse me, if u equals 7 plus t squared, then du would equal 2t dt.
Mm-hmm.
And I've kind of sped up by, I mean, it's really du over dt, and then you multiply by dt. Well, let's take a look at what we have in the integral. What I have in the integral is a t and a dt. So I have this part. So what I like to do is I like to solve for what I have in the integral. And I'll divide both sides by 2 or multiply by 1/2. And I get 1/2 du equals t dt. Okay, that's perfect. So I can make an exchange. This is my t dt, and I can directly substitute in that, the 1/2 du. Now there's probably one other thing that I should take care of while I'm working on this. Alonzia, you see what else I should take care of while I'm doing this substitution?
Your limits, your limits.
Okay, good. Our limits. So let's do the limits. So there's going to be u of 3, which is going to be 7 plus 3 squared, or 16. And u of 7 is going to be 7 plus 7. Is that right? 7 plus 7 squared?
Yep.
Okay. 7 squared, which is going to be 56. Huh. Kind of disappointed. I thought figure out something that worked out pretty nice, but apparently not. Okay, well, let's keep going then. I can rewrite my integral. Oh, there's one other thing I need here for my integral. 1 over the length of this interval, 7 minus 3. So it's going to be 1 over 4 times the integral from 16 to 56. Boy, that's just looking weird. Well, this blue part here, t dt, is now going to be 1/2 du over the square root of u. So the 1/2 can come out in front, and that'll multiply the 1/4 to give me 1/8. Let me rewrite the integrand as something a little different. Any suggestions as to what I could do here for u?
To the negative 1/2.
Thank you, Elise. To the negative 1/2. And from there, we'll find the antiderivative. That will come up here. 1/8 times, that's going to be u to the 1/2 divided by 1/2, evaluated between 16 and 56. So that's going to be 1/4 of the square root of 56 minus the square root of 16, right? Because the 8 times the 1/2 gives me 4, and then just plug in the limits. Square root of 16. So basically, to me, it looks like square root of 56 over 4 minus 1, which is 1/4 of 4. Now, I don't know as though WebAssign's really going to care if you get creative and fancy with this. You could write it as 2 square roots of 13 over 4, and then simplify that, for a final answer of square root of 13 over 2 minus 1. But, the important part is getting right here. And that's the important part. Yeah, I guess I kind of expect you to simplify the square root of 16, but this is really the big important part here. Yay. Okay. How are we looking on with that one? Any follow-up on that one? Let me just check all my participants here, make sure you're all unmuted. Okay. Anything that maybe I went through a little too fast and you want to see again or have some more detail added to it?
It was fine.
Okay, great.
I'm going to go now, by the way.
Okay, that's all right. Thank you. Were there any more questions on things here, specifically to section 6.5? So this is the last new section for you for this edition of this course. You're kind of lucky that I chose not to do section 6.3, which is another volumes of revolution, this time by shells. But let's apply some of what we know to current crisis that we're facing, which is the COVID crisis. So what I have here, starting on March 21st, is the number of new cases per day that we've experienced here in Michigan. So I don't know if it matters to you to see all the data or not, but the interesting thing is that you can fit a model to this, and I chose to fit a cubic model. So let's take a look at what that cubic model looks like. Let's see. Okay, here we go. So looks something like this. And the nice thing is that we do hit a peak and we come down, but the bad news is that the last 2 days have been up a lot. So last 2 days have been bad news. And in particular, if you look at this curve a little further out, something, oops, something bad happens, and let's see, is this one it? No. That is the curve starts to come up. There you go. So that's bad because we don't want to see it trending up. Of course, this is just a calculation. It's not necessarily a prediction. But let's take a look at some of the things that are relevant to us here in this class. So if I wanted to find the area underneath this curve, in fact, what I could do is find the average value of this function. And that would tell me on average how many people per day are contracting COVID, how many new cases. So what I'd want is the area. And let me see where I have that one. I think that one's here. Yeah, so if I scroll, then what you're getting here is the area. So how would I find the average number of cases per day? I've got the integral from 0 to 31. How do you think I'd find the average number of cases per day? What else do I have to do? Well, this is just like the previous two problems. You would have to divide both sides of this, or you have to divide the integral by the length of the interval. So it'd be 31 minus 0, or just 31. And that calculation, that calculation is right here. So I take the integral and divide it by the length. Now let me do something kind of fun for us, and that is, let's take this, and alongside of the graph, I'm going to plot the average value of the function. And we'll see how the average value changes. So the average value started out negative because the function did, but it quickly grows. And the average value is going to continue to grow until we get about here, right, where the function hits its peak. Then the average values should start declining a little bit until we get to the final average values. So on average, over the last month, we've been getting about 1,000 cases a day, is what this is saying.
Wow.
So how are we looking on that one?
Yeah, that's pretty cool.
Okay.
Yeah, definitely.
Now, let's do a couple more things in terms of some calculus and some reminders, because as I get closer and closer to your final exam next Thursday, I'm thinking, I don't know as I can give quite the traditional final exam, and I'm kind of distressed about that, but that's going to be my problem to worry about. Well, let's take a look at some things in terms of review. So I'm going to get rid of the average value here, and let's take a look at the derivative here. So there's the graph of the derivative. So what's the derivative telling me that's interesting? Well, the derivative tells me how the function changes, right?
Mm-hmm.
So let me just shut these two off for a second and focus on the derivative. And in particular, there's an interesting point right here about day 14 of this crisis. The derivative is 0. What does that tell me about this function that I've used?
It's a local min or max at that point.
Excellent. It's a local min or
Local
max.
max.
Yeah, and in fact, because the derivative was positive to the left of it and negative to the right of it, so it was increasing and decreasing, it has to be a local max. So cool. So that's a local max. Let's take a look at the second derivative. Now the second derivative is kind of shallow, so I have to, let's see if I can expand things in the y direction. So I'm going to distort the graph a little bit for just a moment. There we go. And let's think about what the second derivative tells us. What does the second derivative tell you about a function?
Whether it's like concave up or concave down?
Concave up or concave down. And so there's an interesting point right here on the graph at day 24. And let's think about what that point is telling us. So that's where the second derivative is 0. So, okay, second derivative is 0. What's that tell me about my function?
The local min, maybe?
Inflection point.
That's an inflection point. Thank you.
Of course.
All right. So the first derivative would tell us local min or local max, but the second derivative is telling us an inflection point. What's an inflection point? Let's take a look at the graph again. Let's see if I can't pull that up. G of x. There we go. What's that inflection point? Well, that inflection point occurred around day 24, so somewhere around here. And what it was saying is that the shape of the function has changed. Now, a second derivative less than 0 tells you what kind of a shape for the function. Be concave down. I would strongly suggest you know this, say, I don't know, a week from now. So concave down, and you can look and you can see, yeah, this does look like it's a concave down shape. Concave down, my rough hand way of explaining it is concave down is a shape that spills water, concave up would hold water. So if you had a parabola like y equals x squared, that's going to be concave up everywhere. That would hold water. This shape is going to spill water until we get to right here. And unfortunately, what that's showing is that there's a slowing down of the rate of decrease. It's not decreasing as fast as it was a couple days ago because the model is kind of starting to want to turn up a little bit, which is distressing. I'm hoping that today's numbers are much lower and they continue this trend and help drag this curve down towards 0. But, you know, we'll see. The calculus part of it is that the second derivative is telling you what's going on with the shape. Is it concave up or concave down? And the point at which the second derivative is 0 is where the second derivative reflects an inflection point, a change in the concavity. So, all right, good stuff. Good stuff. I think that exhausts all the stuff that I had planned here for this. I think we've milked that for about as much as we can. So let me pause the recording here. Is there any other comments on this before I pause the recording?
So when you show that the graph starts to go back up when you forecast it into the future, is that the second wave of this that they're talking about?
You know, I would love to say that my model is that smart, but I don't think it is.
Okay.
What's happening here is that I just fit a model to the data. I chose a cubic model. I could have chosen an infinite variety of models. But that cubic model, I mean, that is eventually going to have a curve that bends it in the opposite direction. You usually get these kind of shapes. So it's just doing what cubics naturally do. And that is they have a little dip where they're increasing, decreasing, then increasing again. And that's what we're seeing here. It's not a genius of a model. I am hoping that it comes down. It'd be a pretty big coincidence if this somehow predicted a second wave. Although I am worried about people starting to relax their guard a little bit. I think it would take a while before we would see that trend because there's a lag between when you contract the disease and when you get tested and become part of the official statistics. So, I don't know, this curve has to stay flat for a long time before I would feel comfortable saying, okay, you can start to move out carefully.
So are these the same kind of models though that they're using to predict the different levels of infection in the state?
I would think they're using much more sophisticated models. I chose this one because the function that I chose is very accessible. We're familiar with polynomials. There's a lot of different kinds of models that you could use. Yeah, just tons. So This one is
So-
particularly unsophisticated.
So Lisa is one who worked in engineering for years. The math gives us a model to use, and then we get data, and that's statistics. Statistics is trying to marry the two together. And so what's happening now is every day they get more data. And Jeff and then the people who are working on this full time, their model gets updated every day as they get all the data in from all the different counties and hospitals and stuff. The reason why we had an inflection point there at the end was if you look at those last two data points, earlier this week we would have predicted that they would be actually below, say, I don't know if it's 500 there, Jeff.
Yeah.
And instead they're up.
Yeah.
Yeah.
And so
Let me delete these last two data points here. And now take a look at the model. It's predicting that, like today, we should be down to 0 cases, right?
Right.
Well, yeah. So one of the problems in statistics is going beyond your data and predicting things farther out. So I add in the data from 2 days ago, and then it doesn't look as good. And then I add the data from yesterday, and that's when it really starts to pull this curve back up again. So yeah, I was disappointed to see results here and here.
I just am asking because I'm really interested in all this, and it's kind of fitting into like the science path that I am interested in going into. So I'm finding this like super interesting right now.
Cool. Well, that's great. You know, one of the places that you get exposed to this kind of stuff is studying epidemiology.
Yeah.
And that's a cool place to be. It brings together a lot of statistics and a little biology. It's a neat course. A neat discipline, really. You can get a degree in epidemiology. And I remember taking a course in graduate school and really enjoying it.
Yeah. I'm thinking about looking into that. So.
Yeah. Good. Well, I'm going to pause things here. This has been a great discussion. Whoops. I don't want to end the meeting.